Hi, recently I'm very interested in the topic of community detection, and so I have been reading some articles in this topic, and I came across this paper, which is actually written by one of the professor at UCLA, and I have actually met with this professor in person. So I'm honored to learn from Professor Amini, uh, and today I just want to show what I have learned so far by reading this article. And actually, if you Google stochastic block model, actually the post is also quote is actually citing this paper for one of the advanced algorithm to calculate the to maximum the log likelihood. So I think this professor and this algorithm is like uh, very I think they're very awesome. So that's why I want to talk about and share what I have uh, I have been replicate the codes for this from this algorithm. So basically, this algorithm is for stochastic block model. So you want to maximize the likelihood that you can maximize the probability that to generate so that you can generate a network that is more similar to what you have observed, so that you can produce the community based on your observed data. So if you're interested in the details, I would suggest you can read this go through this article, and then I will just demonstrate some of my codes based on the algorithm proposed in this article. So basically, this is the log likelihood that you want to maximize so that you can generate your observed network. And then there's a range of setting that you need to define based on your initial label. So that's the thing you need that the algorithm is based on. So the algorithm, so that if you produce a good initial label, then you will get you'll get a better result faster, or you are more likely to get a better result. But the algorithm would depend on your initial label. So that's why you also need to make sure your initial label is not too far from your so it's good enough to work with. And here is the step for this pseudo-likely algorithm. So basically, you need to initialize by the label E and then a range of setting, and then calculate based on calculate the block sum, and then update based on your initial labeling and your block sum, and then update the probability the proportion for each in each for each group and nodes, and then update the parameter, and then reassign your initial label, then update the probability, then you repeat t times until well within for these two steps you need to wait until the estimate converge, and then repeat a number of times, and then it will give you the final community label. So based on the algorithm here, based on the formulas and the algorithm here, I have been coding to replicate this algorithm in R. So I call this so I use the data set in this two library. So so the data I'm using is called the Karate network. So think um, I think I'm able to plot the connection if okay, yeah. So here is actually the connection. So basically what you have is that you observe a network, which is the nodes and the edges, but you don't but pretend you didn't see the color. So basically, everyone has the same color, and actually, it's not this well separated. So different nodes they're all mixed together, and then you can and then your goal is to you draw so that you can separate um, these two groups, even if they are edges or they are connected between different their connectivity between different groups. So the goal is that we need to find out the label. For example, for these nodes, we need to assign them like they're group 1, and for these nodes, we assign them as group 2. So the goal is to set similar to clustering, but it is based on the network or the connectivity that you assign them a cluster. So first of all, let's create adjacency matrix, and this is the true label, so which is already based on the color here. So the blue color will so the color gives the true label here. And then the nodes, we have 34 nodes, and then we have 2 community here. So and now I have another data set for testing, which is a larger and more complex. So I'll show a little bit later. And the first step is that we based on the algorithm, we initialize the initial label. So here I'm using this this method, which is covered in this in 2.3.1. So that you use the normalized Laplacian, and then you do the you take the eigenvalue, and then you get the first and then so basically just spectral clustering. I've also talked about the spectral clustering in my previous video. So if you're interested in the topic, you can review that video for spectral clustering. So now I just go run the code here to initialize my label E that to start with. And now actually you can see that if even look at this confusion matrix, you can see that there's only one node that is not correctly classified. So that means that like even if I'm not using this pseudo-likelihood method for this network, I'm already getting a very good classification based on just simply using the spectral clustering. And there's only one node that is misclassified using this method. But surprisingly is that when I'm using this pseudo-likelihood method, I actually get 100% matching to the true label. So this is actually the true label, and this is what my initial labeling. So you can see that there's only one node that is misclassified. So this the true labeling is actually group 1, but in this using the spectral clustering, I assign this nodes in group 2. So now let's proceed to this algorithm. So based on the now I'm going to create some matrix based on a range of setting, which you can find it here. And then if you are interested, and basically I'm just replicate exactly what is showing in here, so that you can read this article later, and if you want to know, if you want to also code the same function here, or the formula. So now I'm just going to run everything here to start the actual algorithm. Okay, so here I have all the setting. Done for my for this part. So with all the setting complete, then I can proceed to this algorithm to calculate the block sum and to update these estimator. So I have actually written this in a for loop. So basically for all the loops, so for each iteration, I need to calculate the pi hat, which is this one, update the pi hat, and then update these two parameters, and then until they converge, and then reassign the label, initial label E, So now I'm just running for time t equal to 5. So I'm just running 1 up to 5 times for this algorithm here. So this is the times, and then within each loop, I'm checking whether these two estimator converge, and then reassign. So now let's take a look at my actual result. So so as you can see that this nodes has actually converged or reassigned to group 1. So now let's take a look. So you can see that my output is actually a perfect match with the true label. So even for my initial E, there's one node's misclassified, but after this algorithm here, actually that nodes has been reassigned to the correct labeling. Okay, so now let's. So I really think this algorithm is awesome, and then it is very cool for this community detection. Since if you want to maximize the likelihood, it is NP hard. Basically, you need to search all possible solution, which is like I think the term is intractable. But using this pseudo-likelihood method here, by assigning an initial label, then do some algorithm, then you can get a very good matching to the true label. So now I'm going to run on the politic data, which is actually the data shown, which is another data, which is the data set that is used in this article. So basically is this one here. So you have like something like more than 1,000 nodes, and then their connection between each other. And then if you want to know more about this data set, you can read this article, and then there are also lots of people using this same data set to prove or to uh, for their article. So now I'm just go over the same process here. And one thing that is different from what I've just shown using that small data set is that even so there's a different step for my initial labeling, and also I'm also using the second algorithm in this paper, which is to correct the degrees, which is for a network that is there for the sparse network. So if you're interested in the detail, you can go over. I would really suggest you to go over this article and to learn more about the algorithm and the model. So actually, the model, the algorithm I'm running is including this theta here, which is for the degree correction. And now let's go back to the spectral clustering. So I'm using the method that is proposed over here. So since the network is sparse, so that if you do the normal spectral clustering, you will very likely to collapse some of the nodes to the empty space, so that when you do the eigenvalue, there's no way to calculate. So basically, the idea here is that you added to each entry in your Laplacian that a very small number here, which empirically this is getting this small number is getting empirically, and then you add this number to your adjacent to your actually the adjacency matrix, and then you do the normalized Laplacian, and then you follow the normal spectral clustering uh, algorithm. So since the model, the network, the dataset is bigger, so it might take some time. So as you can see, it might take some time to generate some of the matrix in this algorithm. So, like I said, there are lots of zeros in this adjacency matrix, which since it is a sparse network, so you need to add a small number to each entry in this adjacency matrix so that you can improve your performance. And then you just follow the regular spectral clustering method here. So now there are different ways to do spectral clustering. So it's just up to you to decide which ways you want to use. So now I think I'll just use this one. So get the eigenvector. Need to get the eigenvector for this normalized Laplacian, and I will use this one. So this is actually proposed in this paper to use k minus 1 to get the k, which is the number of community, to get the number of eigenvalues and eigenvector that you want to use to calculate to do the clustering. And here I'm using k-mean. So if you're interested in this, in the spectral clustering, you can take a look at my previous video. So now let's take a look at there will be some misclassification, as you can see that there's some difference in the off diagonal here. So which means that there's some, it's unlike my previous example, it is not like a very very good result in my initial labeling. So now let's proceed to desetting again, and then since this is a large network, it might take some time to run. So if you are watching the video, you can forward the video to skip the wait time. And then I will post the link of this article under the description, and it might take some time, or if it is going to take longer, then I will just stop the video here, and I will just so basically you do the same, get the setting for the to prepare your algorithm, and then run the algorithm to update your parameter. So you might want to increase the number of let's just run for t equal to up to 5 times, and then let's take a look what's the result, and then you can improve your performance from there. So this algorithm, I really think it is very awesome that you basically just do some updating, and then you can get like the previous example, I get a perfect match. And that also work for as aim to increase the performance, to improve the performance for a sparse network, which means there are variation in the connectivity. Some of them are connected, some of them are disconnected. And then it's also conditioning on the degrees, so that you will find two versions in the stochastic plot model. One is the standard, the classic one, and the other is to correct the is degree corrected. And actually, I think in this article it also points out that you don't need to you only need to update a number, like a few iteration, and then you will actually get a very good fit for very good clustering for your label. Okay, so it's still running. So if you want, so if it is for a very large and sparse network, then you probably want to get a better machine and to run this algorithm. to get the result. Since it might take a while to update the estimator and your initial label. So here the like all the degree corrected algorithm, we introduce a theta to control the degrees for each node, and then you again update the estimator here. Okay. So I think there's this one is just to make sure that when to assign us the same group assignment to each node. And let's take a look. Okay, so maybe I think I need to reverse this. So for all the 2's, name it, assign it to 1, and for all the 1's, assign them as 2. Okay, and I get like you can see that I get about 70% of accuracy between the label I get from this algorithm and the true label that is embedded in this network. So I think this is the algorithm for this from this articles, and I think it is very awesome that you can for this community detection. And again, this method is actually also cited in the Wikipedia for to introduce the stochastic block model. So this is so far what I have learned, and then the program I coded for this algorithm. So I hope you enjoyed it, and then I will continue to study this topic to learn more about it. So thank you very much, and also I just want to thank Professor Amini for this article, his hard work, and I will and meeting him in person. So I will continue to learn about this. So thank you very much.